All right, welcome back. We're going to go through the rest of chapter 3a. So this next topic is finding mass percent from chemical formulas now. So we've dealt with molar mass, but we haven't dealt with mass percentages yet. So let's go ahead and take a look at this topic now. Before we dive a little bit more into this topic, I do want to cover a couple important slides here. So this topic on formula mass, where the definition is the formula mass is the sum of the atomic masses in AMU, which we also know now to be in grams per mole, in a formula unit of an ionic compound. So although for sodium chloride, an example of an ionic compound, because notice the metal and then the anionic nonmetal, a halogen. Within this sodium chloride network, we have these repeating units of sodium and chloride. When we're determining the formula mass or the molar mass of an ionic compound, we don't add up each individual sodium chloride, sodium chloride, sodium chloride, because then we'd have to know the exact size of the sodium chloride crystal. Instead, for ionic compounds, how we represent the molar mass is by this formula mass. The formula mass is only the mass of the formula unit, where the formula unit is the empirical formula of any ionic compound that is the lowest whole number ratio of ions in that compound. So possibly in this whole network, we might have 20 Na and 20 Cl. The formula unit for this whole network is not going to be these subscripts though. Instead, we want the lowest whole number ratio. So the formula unit for sodium chloride is just Na and Cl. That means the formula mass for sodium chloride is just the mass of Na and just Cl. So again, we're not adding up each individual Na and Cl in this network. We're just using this for its simplest form. So the simplest ratio here, 1 Na and 1 Cl, just repeating again and again. So with the formula unit, with the formula mass, we can still say the molar mass then of sodium chloride is 58.44 grams per mole. So that doesn't change. AMU is still equivalent to grams per mole. So for ionic compounds, what we've seen from chapter 2 is that the ratio from cation to anion is not always just 1-to-1. For example, if we have cesium here and sulfur, the simplest whole number ratio here is for this subscript to be 2 and this subscript to be 1. So this is the formula unit. So the formula mass then would still be 2 cesium and 1 sulfur. Another example here where these subscripts are not 1-to-1, so calcium and phosphate. So it has to be the simplest whole number ratio, or the lowest whole number ratio, but it's not always 1-to-1. So if this is the formula unit, we would still calculate the formula mass by taking into account 3 calciums, 2 phosphorus, and then 8 oxygen, right? So we've talked about atomic mass, so the mass of just the atom, where elements are made up of atoms. We've talked about the molar mass, which can be applied to talking about a molecular mass and a formula mass now. The molecular mass was when we had the mass of a molecule. The formula mass is when we had the mass of an ionic compound. Here's an expanded look at cesium sulfide. So there's many repeats of cesium, 2 cesiums and 1 sulfur, but again, just the formula unit is the lowest whole number ratio of those ions. So all these ionic compounds are these large crystals usually, but again, just the formula unit is the simplest ratio of the ions that are present, so like CS2 and NaCl. We won't go too much in depth here with mass spectrometry, but I do want you to be at least aware of the idea of this. So the chemical instrument is a mass spectrometer. This is an example of some output data from that instrument. Within mass spec, we have a sample that's vaporized. The vapor is ionized, and based on what we know so far, for something to be ionized means we're converting an atom or a molecule into ions. So remember, ions can be cations and anions, so either positively charged or negatively charged. How do we form ions? We remove or we add one or more electrons. With this output data, what ends up happening is that if a sample is composed of some light atom or molecule and some heavier atom or molecule, when the sample is ionized, light versus heavy molecules will travel at different speeds and end up producing different peaks in this signal output. So ultimately, for mass spectrometry, we are wanting to determine the mass of components that are in a sample. So we'll see unique peaks for each different mass. So each different substance that's in our sample will produce a different peak if they have a different mass. The charge of the ions is also important, so this mass to charge ratio, but again, here is this main takeaway for mass spectrometry. Okay, so now coming back to the topic at hand. To calculate the percent composition of an element within a compound, for example, we might want to know the percent composition of oxygen element in this compound of water. The formula for this is N times the molar mass of the element divided by the molar mass of the compound times 100%. Lowercase n is the number of moles of the element in 1 mole of the compound. So for example, for this case, we would need the number of moles of oxygen in 1 mole of this compound of water. This slide should look familiar from Chapter 3a, Part 1. So we do know how to take a molecule or a compound and say here, for example, there are 10 moles of hydrogen for every 1 mole of this compound. So these subscripts are how we know the mole-to-mole ratio of each element within the compound. Let's take a look at this example here. So percent carbon, hydrogen, and oxygen in this molecule here. So N is the number of moles of the element in 1 mole of the compound. So for carbon, we have 2 moles of carbon for every 1 mole of the compound. For hydrogen, we have 6 moles of hydrogen for every 1 mole of the compound. For oxygen, we have the subscript of 1 that's implied. Then the molar mass of the element here, carbon is 12.01 AMU or grams per mole. Hydrogen is 1.008 AMU or grams per mole. Oxygen is 16.00, about 15.99 AMU or grams per mole. So far we've looked at the numerator here, so N, and then the molar mass of the specific element. Then what we need in the denominator here is the molar mass of the whole compound. For the molar mass of the whole compound, we need to multiply 2 times the mass of carbon, then add that to 6 times the mass of hydrogen, then add that to 1 times the mass of oxygen. Okay, so when we multiply these and then add up the products, we'll get this molar mass of the compound of 46.07 AMU, or 46.07 grams per 1 mole. We know this is our molar mass. Another appropriate term for this would be the molecular mass, since this is a molecule. So that's where we get 46.07 here in the denominator. Then because this is percent composition, we need to multiply by 100%. A really good check to do at the end is we know that carbon, hydrogen, and oxygen all need to add up to 100% of the molecule. So we can take this percentage plus this, and be sure that approximately this is 100%. It could be off just slightly here if we did any different kind of rounding. So it's okay if we get like 100.01, for example. So let's use this formula. Let's use this concept of percent composition. Here for this practice problem, we have the chemical formula for chromium 3 nitrate. Remember what those Roman numerals mean. It means that chromium can form 2 different kinds of cations, but here in this compound, it has a 3+ charge, so hence the Roman numeral 3 there in parentheses. Here we're asked to calculate the mass percent of oxygen in this compound. and then we'll round our answer to the nearest percentage. So we've talked about this definition here. So for example, the mass percent of chromium in chromium-3 nitrate is the percentage of the mass of a sample of chromium-3 nitrate that is the chromium component. So let's say the mass percent of chromium in chromium-3 nitrate were 85%. So if that were true, that would mean that 85.0 grams out of every 100 grams of chromium-3 nitrate would be chromium. How do we get that? Well, 85% of 100 grams. We need to convert this out of a percentage and into a decimal by dividing by 100. So 85% of 100, we end up determining that by taking 0.85, so 85% divided by 100, then multiplied by this mass, so 100 grams. It's important here we note this is grams because we're dealing with a percent by mass concept right now. So percent composition, think percent by mass. So you can see it's an easy, convenient way to assume 100 grams of the compound in total, because then if we have this percentage, it's pretty easy to say that out of that 100 grams or 100%, 85% or 85 grams is that specific element. We can also use this convenience of 100 grams because the mass percent of each element is the same for every size sample of a compound, no matter how large or small. This relates to this law of constant composition, so another important law here, in addition to the law of conservation of mass. So no matter how large or small the sample is, the mass percent doesn't change, so why would we not use something so convenient such as 100 grams total? Because then that's really easy to correlate that with 100% of the sample. So for another point of convenience, we remember the molar mass is the number of grams or how much 1 mole of a sample weighs. We're going to conveniently assume 1 mole of the compound in total. So we're going to combine this with assuming that we have 100 grams starting, and we'll also need to use the molar mass of the elements and the compounds like we saw on the previous slide, so that equation. The takeaways here, we're going to assume 100 grams of the sample in total and 1 mole of the compound in total. Let's apply these and do practice with them. So now applying this mole of a specific element to the mole of a whole compound, this means there is 1 mole of chromium for every 1 mole of chromium-3 nitrate. Why is that again? We remembered this subscript of 1 is implied. For a challenge, I want you to also write out, for practice, how many moles of nitrogen and oxygen there are per 1 mole of chromium-3 nitrate. So for nitrogen, there are 3 nitrogen atoms, so we would say 3 moles of nitrogen for every 1 mole of chromium-3 nitrate. Oxygen, there are 3 and 3. So for oxygen, we have 9 moles of oxygen for every 1 mole of chromium-3 nitrate. Okay, so we use those subscripts and remember what the meaning is for a subscript to be outside of the parentheses. This is a little bit of a review from chapter 2. So remember, when we're writing out the formulas with polyatomic ions, we are really careful to note where we put those parentheses and where we put those subscripts. So a good way to approach this problem is exactly what we started with. So figuring out the moles of chromium per mole of chromium-3 nitrate, figuring out the moles of nitrogen and oxygen. So 3 moles of nitrogen, 9 moles of oxygen because of this chemical formula here. Now for an added challenge, you might be also given just the name of a compound, and then you have to write out this formula, and then you would also need to figure out these mole ratios. So one of those convenient factors is saying that we have 1 mole of a sample of chromium-3 nitrate. So 1 mole of the full compound, 1 mole of the compound, 1 mole of the compound. That allows us to write out these mole ratios here pretty easily. So 1 mole of chromium, 3 moles nitrogen, 9 moles of oxygen. From this formula, we know we also need the molar mass of each element and the molar mass of the whole compound. So next here, we can multiply the moles of each element by the element's molar mass. So 1 mole of chromium, here is the molar mass or the atomic mass of chromium based on the periodic table. Nitrogen 3, here's the mass of nitrogen. Oxygen 9 moles, here is our atomic mass of oxygen. To figure out what units we have here, so we see this mass in grams, let's prove that we should have a unit of grams. So here we have 9 moles of oxygen, and we're multiplying it by its molar mass, which is grams of oxygen per mole of oxygen. So mole of oxygen and mole of oxygen cancel out, and we have this times this. We're left with just units of grams of oxygen. So that's how we get these values here in this table, so these answers here, in just units of grams. So after that, we can add the masses of all the elements to find the total mass of 1 mole of chromium. 3 nitrate. So we need the molar mass of the whole compound, but we have the individual components, so we can just use those to add up to get the molecular mass of chromium 3 nitrate. So this 143, for example, was already 9 oxygens, so 9 times 15.99 gave us this. So when we add all these up together, it's already taken into account the subscripts on chromium, nitrogen, and oxygen, how many atoms there were in the molecule. So the total molecular mass for chromium 3 nitrate is here. Back to our formula then, we already have the product here for the numerator. Then we also just figured out the molar mass of the compound. So we need to take each one of these, divided by the molar mass of the compound, then multiply by 100%. So for chromium, the product, so what would be in the numerator, 51.9961, divided by the molecular mass or the molar mass of the whole compound, so 238.0112 times 100%. These values in the table so far are not yet multiplied by 100%, so they're still in their decimal forms. So now we take each of these values, multiply by 100%. Note that before we multiply by 100%, these should all add up to 1. So this is sort of our mass fraction or mass ratio, not yet in a percentage. And note that, again, all of these should add up to 1 because that's the total. Then 1 times 100% equals what this should total up to as well. So all these percentages then should also total up to approximately 100%. We went through this practice for each one of these elements. In the original practice problem, we were asked about oxygen specifically. So now our final answer here is 60%. We were also told to round to the nearest whole number, the whole number percentage, so 60%, rather than 60.049%, for example. So 60% is our final answer. So I was mentioning how we should also conveniently assume we have 100 grams of the compound in total. So we're going to do a practice problem using this convenience factor now. So we're going to first convert the mass percent of each element into grams of each element. So this is when we're starting out with a mass percent, and we want to end up with an empirical formula. So we're about to do an example with this. Then we're going to use the molar mass of each element. When we're going from a gram amount and we're using a molar mass, it's to get us into moles. Once we have these mole amounts of each of the elements, we're going to look for the smallest number of moles in order to get the simplest whole number ratio. And again, we're going to go through each of these steps in an example. If the subscripts are not whole numbers in the end, whole number integers, we will definitely need to change those into integers. Then at the end of all this, we'll have an empirical formula from starting out at a mass percent. So let's talk through this. So this topic we're going into now is on elemental analysis. So here in this problem, we are given a mass percent of carbon, hydrogen, and oxygen. And from this composition table, we're going to figure out the empirical formula of this compound X. Okay, so we're going to kind of work backwards from the last example we went through. So for this practice problem, we're going to need to remember the definition of an empirical formula. So this is a chemical compound, the formula for a chemical compound that shows the number and types of the atoms in each formula unit of the compound. For example, if we had a molecular formula that's C2H4, to convert this into an empirical formula, we would take these subscripts and go from C2H4 to the simplest ratios that we can go for, so CH2. Both 2 and 4 are divisible by 2, so we divide those subscripts to get the empirical formula here. So from our practice problem, we know that the formula has carbon, hydrogen, and oxygen. Based on the order of how we list these, we always put hydrogen right after carbon, and then oxygen is a group 6A element, so this is going to come after hydrogen. This is our basic skeleton for this empirical formula with carbon, hydrogen, and oxygen, and then we need to figure out what these subscripts are to actually determine the empirical formula. So we know these elements are present, but we don't know these subscripts. We don't know these mole ratios. And we'll practice this too, but it's going to be important that A, B, and C, we simplify those and they're reported as whole number integers. Okay, so you won't see decimals here. You'll see whole numbers for A, B, and C. So the way we read this A to B to C is really like we're saying the atoms of carbon to the atoms of hydrogen to the atoms of oxygen. Similarly, when we connect that the compound is 1 mole of this whole compound, so if we had 1 mole of this whole compound, then what we can also say is that the moles of C to the moles of H to the moles of O is also going to be some ratio of A to B to C. We don't yet know the numbers of A, B, and C, right? We need to figure out those subscripts, but what does hold true is that we should be able to multiply each of these subscripts by the same whole number and still end up with the same result. So A might be 2, B might be 1 or 6, C might be some other number. Regardless of what A, B, and C are, this ratio holds true. And then also if we multiply each of these by 3, this ratio also holds true. We can also divide A, B, and C all by the same number, where this ratio would also hold true. And again, we don't know what A, B, and C yet are, but we're going to figure out what these subscripts are. So we're going to use those mass percent values that were given in the problem to find a mole ratio of the elements. And from that mole ratio, we can then deduce the atom ratios of the elements in every sample of this generic compound X. Right now, our generic compound X is C sub A, H sub B, O sub C. So we talked through these steps in this flow chart. Now let's practice them for our specific problem. So step 1, imagine we have a sample of compound X. We're going to assume it weighs exactly 100 grams. In the problem, we were given these mass percentages, so 41%, 4.58, and 54.6. When we assume the total compound weighs 100 grams, and remember the mass of a sample is totally unrelated to its molar mass, right? So we can weigh out 100 grams of compound X. This doesn't tell us anything yet, though, about the molar mass. So right now we're just assuming that we weighed out 100 grams. With these percentages then, we want to find 41% of 100, 4.58% of 100, and 54.6% of 100. To solve for this, the first thing we want to do is take 41.0% out of a percentage, and we do so by dividing by 100. That's going to equal 0.41. Then we take 0.41, the decimal form of this number, and we multiply it by 100 grams. That's going to equal 41.0 grams. So carbon having a mass percent of 41.0, when we conveniently assume that the total compound weighs 100 grams, then the mass of carbon is going to be 41.0 grams of that total 100 grams. So we have 41.0 grams. We can do the same for hydrogen and the same for oxygen. Next, in step 2, we're going to divide the mass of each element by the element's molar mass to find the moles of each element in the sample. This comes back to what we did a lot in chapter 3a part 1, where we want to go from a gram amount to a mole amount. And to do so, we use the conversion factor of the atomic mass or the molar mass. When we go to the periodic table, we'd find the atomic mass of carbon is 12 grams per mole, hydrogen about 1.008 grams per mole, oxygen 15.994 grams per mole. To show you how those units work out, let's take 4.58 grams of hydrogen. If we have the molar mass of hydrogen is 1.008 grams per mole, how do we need to orient this conversion factor in order to leave us with just moles? Well, we need to put grams in the denominator, so 1.008 grams per mole of H, grams of H if we're being super consistent, grams of hydrogen cancels out, grams of hydrogen cancels out. We take 4.58 divided by 1.008, left with just units then of moles of hydrogen. So that's how we get this mole amount of 4.54, because essentially we're taking 4.58 almost divided by itself, divided by 1.008. We should repeat this for carbon and oxygen as well. Then after step 2, we have moles of carbon, moles of hydrogen, and moles of oxygen, all from the assumption that the total mass of our compound X is 100 grams. Again, we don't yet know the molar mass of the compound. Now in step 3, divide the moles of each element by the smallest number of moles of any element to find the mole ratios. What does this mean? So for the mole amount, we had 3.41, 4.54, and 3.41. Right, so 3.41, 4.54, and 3.41. What we're doing in step 3 is identifying the smallest number out of these options. So 3.41 shows up twice. 3.41 is smaller than 4.54. So now we divide the moles of each element by that smallest number of moles. So we're dividing 3.41 by 3.41. We're dividing 4.54 also by 3.41, then dividing 3.41 again, divided by 3.41. When we do that, we get these numbers here of 1.00, 1.33, and 1.00. We're getting closer now. I mentioned towards the beginning that we want to report these as whole number integers. So now to figure out how to report these as whole number integers, in step 4, we multiply the mole ratio by the smallest whole number that changes it into a whole number ratio. We have to kind of do some guess and check here. For example, 1.33. When we multiply that by 2, that comes out to 2.66. That's still not a whole number ratio. It's still not a whole number. So 1.33 times 3, well, we're getting closer now. That is approximately a whole number. So 3.999 is approximately 4. So we needed to take this non-integer value, this decimal number, and kind of guess and check and multiply it by these different whole numbers, because in the end, we need all of our subscripts to be whole numbers. When we decide that 1.33 can be multiplied by a whole number of 3 to have this be a whole number, then we need to repeat that for our other mole ratio values. So we need to take 1, also multiply it by 3. So by 3. We need to take 1.33, multiply it by 3. We need to take 1 and multiply it by 3. So you have to do this for every mole ratio that's present. We use the decimal form to figure out this 3, but then again, we carry this to all the other mole ratio values in the problem. With that, this 3 times 1, this comes out to a whole number. 3 times 1.33, approximately a whole number, pretty darn close. 3 times 1, 3. So this is what we got in step 4. Now we're ready to put this all together. So we had C, H, and O with these unknowns of A, B, and C. now what we just figured out through steps 1 through 4 is what needs to be put in for A, B, and C. Our final answer comes to C3, H4, and then O3. So we took mass percent values and we ended up getting this empirical formula. We confirm it's an empirical formula because we can't divide 3 and 4 by any whole number. They're not both divisible by any other number aside from 1. So this is our final answer. This is the simplest whole number ratio, therefore confirming to us that we do have this final empirical formula for compound X. In the main slide deck, I included this table for you. This is good practice to take the term atomic mass, molecular mass, formula mass, and molar mass, and to recognize that atomic mass is for atoms, molecular mass for molecules, formula mass for ionic compounds, and molar mass can be used for terminology for any of the above. AMU, we know, which is the same thing as grams per mole. Then we also reviewed Avogadro's number in Chapter 3A, Part 1. We're going to continue using this throughout. So we just went through that past topic. We're going to go through this one that will be more of a review. So finding a molecular formula again from molar mass and elemental analysis of binary compounds. In this practice problem, we have compound X. It has a molar mass. Now we're told that this time. In addition to knowing this, we're also told that phosphorus has a mass percent of 39.17, sulfur 60.83%. So it's a little bit different than what we've seen before, but it will feel similar, except now we're given a molar mass and this table. Let's figure out how to approach a style problem like this to then write out the molecular formula for compound X. Also for this one, we're writing out a molecular formula and not an empirical formula. Okay, so we're writing out a molecular formula, not an empirical, so let's see how we differentiate these processes. So to find the molecular formula, we're going to need to know the molar mass and an empirical formula. Previously, we used these mass percent values in a table to find the empirical formula. Now we're going to go from an empirical formula into a molecular formula. We're going to, again, use this convenience factor of assuming 100 grams total. So let's go ahead and execute this part now. So we're going to assume 100 grams total. So the first thing we need to do, so following steps from the last example we went through, we want to find 39.17% of 100 and 60.83% of 100 grams. So 39.17% divided by 100 is 0.3917. Now we take 0.3917, multiply it by 100 grams. This tells us for phosphorus that out of 100 grams of the total compound, 39.17 grams of that is going to be phosphorus. At this point, we can do the same thing for sulfur, or we can take 100% minus 39.17% because there's only two different elements present. There's phosphorus and sulfur. So whatever is not phosphorus has to be sulfur. So that's how we get 60.83% here. And from that 60.83%, that means we have 60.83 grams. So here we could have taken, instead of percentages, say 100 grams minus 39.17 grams, because the remainder of this is going to be sulfur. So that's how we get these numbers here in this column. So now we have 39.17 grams of phosphorus, and we're going to need the atomic mass of phosphorus. To practice doing this, we're going to go to the periodic table, find phosphorus. It has an atomic mass of 30.974. So 30.974 grams of phosphorus per mole of phosphorus. We need to orient this such that we cancel out grams and we're left with just moles. So grams of phosphorus cancel out, we're left with just moles of phosphorus. Essentially, we're taking this gram amount and we're dividing by the atomic mass. I like to write it out like this so I can see exactly what units are canceling out. This gives us 1.265 moles of phosphorus. We repeat that for sulfur using the periodic table and the atomic mass of sulfur being 32.065. 60.83 grams divided by this molar mass, cancel out grams, leaves us with 1.897 moles of sulfur. Now this should again sound familiar from the previous example we did. Next, we want to identify the smallest mole amount. So 1.265 is less than 1.897. That means we want to divide each of the mole amounts, 1.265, by 1.265, and divide 1.897 also by 1.265. When we do that division, we get these numbers of 1 and 1.5. 1 is a whole number, 1.5 though is not yet a whole number integer. So 1.5, can we multiply that by 2 to get it into a whole number? Yes. So we didn't even need to try any other numbers. When we multiply this non-whole number by 2, we get a whole number. That means we will also need to multiply this also by 2. So we're multiplying both mole ratio values by the same value here. So multiplying both by 2 to get these mole ratios then of 3 and 2. So to keep track, sulfur then has this mole ratio of 3, phosphorus 2. So that is shown here in this step. With this ratio now of 2 to 3, we can go ahead and plug in these subscripts. 2 was referring to phosphorus, 3 was referring to sulfur. To summarize at this point, we know the empirical formula for our compound. We went through the steps like we did for the previous example. We ended up with an empirical formula. For our practice problem in this topic, though, we were also given a molecular mass, and we're asked to actually find the molecular formula. So P2S3 multiplied by some whole number n, we need to figure that out now, is going to give us our more complicated molecular formula, right? So a molecular formula doesn't have to be the simplest whole number ratio here. Those subscripts are going to be something greater than 2 and 3, or I should say those subscripts could be something greater than 2 and 3, because a molecular formula, again, doesn't have these simplest whole number ratios. So we need to combine our knowledge of our newly found empirical formula and the molecular mass to find this molecular formula. I mentioned we need to find out what n is. So here we have the molecular formula is equal to the empirical formula times n. We can make another connection here as well. So the molar mass is going to refer to the molecular formula, whereas the empirical formula molar mass is the mass that corresponds with the empirical formula. For the empirical formula, for example, P2S3, that's going to be some molecular mass where we multiply 2 times the mass of phosphorus and 3 times the mass of sulfur. From this empirical formula, though, one example of a potential molecular formula could be P4S6. So if this is the empirical formula, this is one possibility for its molecular formula. The molecular mass of P4S6 is going to be different than the molecular mass of P2S3, of course, because there's 2 additional phosphorus and 3 additional sulfur. This formula here is making that connection. So the molar mass of the molecular formula is going to equal the empirical formula molar mass times n, some whole number. To get here, I just use an arbitrary n of 2. We multiplied these subscripts each by 2. We don't know n for our specific problem though, so we need to figure that out. Rearranging this equation will have n is equal to the molar mass divided by the empirical formula molar mass. The molar mass is told to us in the problem. For the empirical molar mass, we have our empirical formula, that's P2S3. Phosphorus, again, weighs 30.97. Sulfur weighs 32.066. For the empirical molar mass then, P2S3, we need 2 times the mass of phosphorus and 3 times the mass of sulfur. And again, this is for our newly found empirical formula. That comes out to be about 158.14 grams per mole. So now that we have the molecular formula's molar mass from the problem and the empirical molar mass, we can use this formula to find N. 316.29 grams per mole divided by 158.14 grams per mole is equal to 2. So our N value is 2. That helps us then take our empirical formula, we multiply it by our newly found N to get our molecular formula. So the molecular formula, the final answer then is P4S6. For this next topic now, we're going to go through stoichiometric coefficients. To talk about this topic, we need to cover chemical reactions now. You might hear it called a chemical reaction or a chemical equation, where this is a process in which one or more substances is changed into one or more new substances. So that's the reaction, and for every reaction, we can write out a chemical equation. For every chemical equation, every chemical reaction, we have the term reactants going to products. Reactants are always on the left-hand side, products are always on the right, separated by this reaction arrow. For example, we could have hydrogen gas, H2, react with oxygen gas. Remember, these are both one of the Brinkelhoffs, meaning that these elements exist as a diatomic, so H2 and O2. Here are our reactants, so hydrogen and oxygen. Here is our product, water. Here is our reaction arrow. We show hydrogen being added to oxygen to then show the products forming. What I showed you on the last slide is how we can depict it with a space-filling model. So we talked about these different models. Another way we could say this is 2 hydrogen diatomic molecules would be more specific, plus 1 oxygen diatomic molecule come together to form 2 water molecules. So this is how it can be written out in just words as well. This is what's happening on the molecular level. We have hydrogen gas in white reacting with a molecule of oxygen gas, or O2, to form water. The principle that comes up here is law of conservation of mass. So we're not creating nor destroying anything that's present here from the reactant side to the product side. So law of conservation of mass, importantly, comes back again. More commonly, how we see reactions written out is like this. So 2H2 plus O2 goes to H2O. How we read this, now that we know more about what these coefficients and subscripts mean, we say 2 moles of H2 plus 1 mole of O2 forms 2 moles of H2O. These coefficients out here, remember this is a coefficient, this is a subscript. These coefficients then tell us the number of moles. It's similar to what we saw for the subscripts, but now we're taking one substance plus another substance forming something else. So we can have mole ratios within just one substance and also mole ratios amongst multiple substances. One thing we'll practice doing more is taking the molar masses and these mole ratios to convert moles of each reactant and product into the actual number of grams. When we start to practice these, we will notice that the grams of the reactants must add up to the grams of the products, again from that law of conservation of mass. So regardless, again, the mass of the products must equal the mass of the reactants because mass cannot be created nor destroyed. Let's practice reading more of these chemical equations. From this chemical equation, we can say 2 atoms of magnesium plus 1 molecule of oxygen makes 2 formula units of magnesium oxide. Similarly, using these coefficients to know that they're meaning moles, 2 moles of magnesium plus 1 mole of oxygen makes 2 moles of magnesium oxide. Something mentioned in Chapter 3a, Part 1, when in doubt, work in moles. After working in moles, then we can convert to grams for each reactant and product. A big no-no in how we read out these chemical equations is we don't say 2 grams of magnesium plus 1 gram of oxygen makes 2 grams of magnesium oxide. We don't say that because remember, we're going to work in moles. These coefficients out here tell us the number of moles. We can work in moles and then convert to grams. So working in moles, then converting to grams only by using the molar mass. So we use the molar mass to get these mass values here. Again, we're not going to say that 2 grams and 1 gram makes 2 grams. We're going to talk in terms of moles. Okay, so we're going to work in terms of moles, then we could convert to grams. Let's talk through this practice problem. What is the total number of oxygen atoms on the left-hand side of this chemical equation? This could also be asked on the reactant side. All right, so reactant side is the left-hand side, product side is the right-hand side. So on the left-hand side, we have our reactants. That's why the products are temporarily grayed out here. So then on the reactant side, we can identify all of the reactants that contain oxygen. So if we see phosphate here, silicon dioxide. Next, we need to use our knowledge of what these subscripts mean. For oxygen here, we have 4 oxygens, then outside the parentheses, we have 2. So we need to take 4 times 2 to get 8 oxygen atoms here. Silicon dioxide, we just see 2 here, no parentheses, so that is 2 oxygen atoms. So within phosphate and within silicon dioxide, we have 8 and 2. Next, we use these molar coefficients out front. So there are 2 of everything here. There's 4 of everything here. There's 12 carbon. These are separated by a plus sign. So 2 of everything here, separated by a plus sign. 4 of everything here, separated by a plus sign. So we have 8 oxygen. We need to multiply that by 2. Here we have 2 oxygen. We need to multiply that by 4. This then totals up to there being 24 atoms of oxygen on the reactant side of this equation. So to show this more explicitly, these subscripts we've worked with before, we show these as ratios within a compound. So for every 1 mole of B4H10, we have 10 moles of hydrogen, for example. Well, what about this coefficient? So these coefficients that we worked with in these chemical reactions and equations, these help us tell the ratios amongst substances, typically in a reaction. So again, when we're talking about ratios within a compound, we don't look at these coefficients. We just look at these subscripts. However, for coefficients, we use those for ratios amongst substances or compounds or molecules. For example, if we happen to have this reaction with water, we would use these coefficients to help us write out a ratio like this. For every 3 moles of B4H10, we have 2 moles of H2O. Okay, so to write out reactions like this, we're going to need to balance reactions. We'll practice doing that. But again, coefficients, ratios amongst substances in a reaction, whereas these subscripts help us tell the ratios within a compound or within a substance. So in order to figure out these coefficients between this compound and this compound, for example, we need to work on balancing equations. So that's going to be our next topic. So we're going to balance chemical equations with non-interfering coefficients. We'll also go through an example with interfering coefficients. To balance chemical equations, we're going to go through these specific steps. Step 1, we're going to write the correct formulas. So now naming and writing formulas from chapter 2 is going to be crucial here in balancing equations and writing out equations. For example, we would need to know from the word carbon dioxide, the name carbon dioxide, we would need to write out the correct formula from the name. Okay, so be sure you're practicing naming still molecular and ionic compounds with both monatomic and polyatomic ions. You wouldn't be expected to know ethane. You wouldn't be expected to know that C2H6 is ethane, though. So the common ones we've gone over, you will need to know those, but you won't need to know some of these organic compounds. You should know water. Step 2, change the numbers in front of the formulas, so change those coefficients to make the number of atoms of each element the same on both sides of the equation. Really importantly, we do not change the subscripts, we only change the coefficients. Remember, this is a subscript, this is a subscript. The coefficients are the ones that are found up front. So coefficient versus subscript, we'll change the coefficients, but we will not change the subscripts. Step 3, start by balancing those elements that appear in only one reactant and one product. It'll make it a lot easier. For example, if we have this chemical equation, we see carbon, hydrogen, and oxygen. Here on the product side, oxygen shows up in this product and in this product, so we don't want to start with oxygen. So now carbon only shows up in this reactant and in this product. Hydrogen only shows up in this reactant and in this product. So we could start with carbon or hydrogen. If we're going to start with carbon, for example, comparing C2H6 to CO2. There are 2 carbon atoms here and only 1 here. So this step in step 3, it would tell us to multiply this coefficient by 2. So we have 2 carbons on this side and 2 carbons on this side. So we'd multiply CO2 by 2. Now notice we have this coefficient out front for carbon dioxide. Next, we can focus on hydrogen. It again only shows up in one reactant and in one product. So C2H6, this has 6 hydrogens. Here we have 2. So what do you think we should do to make the number of hydrogens equal? Well, we could multiply this coefficient by 3. So then 2 times 3 becomes 6 hydrogens here and 6 hydrogens here. So now we have incorporated this coefficient here and this coefficient of 3 now. Everything else has stayed the same so far. Step 4, balance those elements that appear in 2 or more reactants or products, so usually that pesky oxygen. So C2H6 and O2, here we have 2 oxygen atoms. Here we have 2 times 2, we have 4 oxygen atoms. Here, 3 times 1, we have 3 oxygen atoms. So this can get tricky. So on the reactant side, we have 2 oxygens. On the product side, we have 7. To make this equivalent, we can actually multiply 2. So 2 over 1 times 7 over 2. How do we get this fraction? We're taking this larger number divided by the smaller number. When we multiply 2 times 7 over 2, that leaves just 7. So making 7 oxygen atoms on the reactant side, 7 on the product side. So this isn't our final answer because we don't like to have fractions here typically in these equations. But here we have this coefficient, then for oxygen, that's trickier. We do have this coefficient, but it's a fraction. How can we make 7 over 2 not a fraction? What whole number do we need to multiply this by? Well, if we multiply this fraction by 2 or 2 over 1, 2 would cancel out, leaving just a whole number of 7. So we can multiply 7 over 2 by 2 to get a whole number. That means we also need to multiply every other one of these coefficients by 2. We can't just multiply one coefficient. So we multiply 1, remember this is implied 1, by 2. 7 over 2 multiplied by 2 is just 7. 2 multiplied by 2 is 4. 3 multiplied by 2 is 6. So we don't have any fractions in these coefficients. At this point, we believe to be done. It is always super important to check your work. To do this, you can make a table like this one, have reactants and products, and then list all the elements that are present. To start out with carbon, we have 2 times 2, so we have 4 carbons on the reactant side. Hydrogen, we have 2 times 6, so that's 12 hydrogens on the reactant side. Oxygen then, we have 7 times 2, that's 14 oxygens on the reactant side. So we checked all these amounts. They have to be the same on the reactants and the product side. They have to be the same amount of each element. So let's do the product side now. For carbon, we have 4 times this implied subscript of 1. So 4 times 1 is 4 carbons. Hydrogen, we have 6 times 2. That's 12 hydrogens. Oxygen shows up in both products. We have 4 times 2 is 8. 6 times 1 is 6. 8 plus 6 is 14 oxygens. Then we have to check that they're the same, and they are. So this is a correct balanced equation. So check your work here for these balancing equations kinds of problems. Let's practice doing these steps for this practice problem. So we want to balance this chemical equation. We know that the principle of conservation of mass is at play, so nothing can be created nor destroyed. Nothing can magically show up on the product side that wasn't on the reactant side. For this example problem, carbon only shows up in one reactant and in the product. Same for hydrogen. So technically we could start with either carbon or hydrogen. If we want to start with hydrogen, we have 2 on the reactant side and 6 on the product side. So to make this an equal number of hydrogens, we can change this coefficient to 3. That would leave 3 times 6, 6 hydrogens and 6 hydrogens. 6 on the reactant side, 6 on the product side. So now we've added this coefficient here, and we can work on carbon. There's 1 carbon here and 2 here. So we can add in a 2 coefficient, a 2 molar coefficient. So there's 2 carbons and 2 carbons. To further reiterate that we never change the subscripts, we only change the coefficients. This is C2H6. That has to say C2H6. This is H2. That subscript will not change. It's always H2. So this is incorrect, and then this is incorrect. And we have talked about how we would balance the carbons out, so we're adding that molar coefficient of 2 here. Again, we only change and balance these chemical equations by changing these stoichiometric coefficients. We do not change the subscripts. After we add in this molar coefficient here, and we had already added this one in for hydrogen, we get this balanced equation here. We should certainly check our work. So for carbon on the reactant side, there are 2 carbon atoms. Carbon on the product side, still 2. Hydrogen, we have 3 times 2, that's 6 in total, and 6 in total. So 6 hydrogens, 2 carbons. This is a correct balanced equation, and we checked our work. Now that equation that we just went through was with non-interfering coefficients. So we're going to go through another example, but with interfering coefficients. It gets a little bit trickier, but we're still going to follow those same steps. Let's take this reaction equation and add in coefficients to balance this. One check I should also mention is that these ratios here, these molar coefficients, are the smallest ratios possible. So 2 to 3 to 1. If we could divide these by some common denominator, we would need to do that for this to be a final correct answer. These can't be divided by anything other than 1 and themselves, so this is the final answer. These are the smallest whole number ratios. So for interfering coefficients, we're going to approach it a little bit differently, still generally the same steps. So we're going to assign 1 as the stoichiometric coefficient of the compound with the most elements in it. If more than one compound has the most number of elements, we assign 1 as a stoichiometric coefficient for any of them. You would hear this called stoichiometric coefficient and molar coefficient as well. Then we'll find an element that appears in only one of the compounds that have unknown stoichiometric coefficients. We'll assign a stoichiometric or molar coefficient so that that balances the atoms of that element. With interfering coefficients, we're going to need to do some trial and error and repeat this a few times. Then similarly, we again don't want any fractions, so we're going to clear any fractions by multiplying the entire equation by some whole number. And we just have that implied 1 for our molar coefficients and our subscripts. So we don't write that number 1 out front, we just understand that it's there. Then of course, we are going to check our work. Let's go through each of these steps for our practice problem at hand. Assign 1 as the stoichiometric coefficient of the most complex compound. There's hydrogen and oxygen here with subscripts of 2 and 1, silicon and oxygen 1 and 2, oxygen just 2. This one, however, has these subscripts of 4 and 10, so this is going to be our most complex substance. So we're going to put a 1 out front there. Step 2, balance an element. So now we're going to look for an element that appears in only one of the compounds that have now an unknown stoichiometric coefficient. Currently, we're adding in a question mark here for ones that are unknown. Remember, we just sort of tentatively and arbitrarily put a 1 here. So oxygen shows up here, here, and here. So generally speaking, working with oxygen is trickier. So let's avoid working with oxygen for now. Silicon would be a good choice because it appears here and it only appears in one other product. It doesn't also appear in this reactant. So there's 4 silicon atoms here because we tentatively assigned this as 1. To balance silicon at this point, we're going to put a 4 as this coefficient in front of silicon dioxide. So now we have 4 silicon and 4 silicon. Step 2, we need to repeat and possibly do some trial and error. So let's balance another element now. Again, working with oxygen is usually not that straightforward, so our only other option at this point is to work with hydrogen. With the coefficients assigned so far, we have 1 and 4. There are 10 hydrogens here and 2 here. So to make this balance out, we can change this coefficient to 5. So 5 times 2 is 10, and here we have 10 hydrogens. What's left then to repeat for step 2? Now we can try to work with oxygen. From these coefficients so far, there are 2 times 4, there's 8 here. There's 1 times 5, so 5 here. So on the product side, we have 13 oxygen atoms. Here we have 2 oxygen atoms. So what coefficient would make sense here? Remember, we put the larger amount here and then the smaller amount here. So there's 2 and there's 13. So 13 and 2. We should put that coefficient here because now we have 13 over 2 times 2. That's now on the reactant side, 13 oxygen atoms to match 13 oxygen atoms on the product side. So tentatively at this point, we have 1, 13 over 2, 4, and 5. Step 3, we're going to clear any fractions, and we're not going to include that number 1 out front. Our fraction of 13 over 2, how do we clear that? Well, we multiply everything by 2. It's really important that we know to multiply 2 all the way through, so for every molar coefficient. 13 over 2 times 2, that's just 13. 2 times 1 is going to make that 2. 4 times 2 is going to make that 8. 5 times 2 is going to make that 10. So here, 2, 13, 8, and 10. We're not quite done because this important step should be part of how we approach this kind of problem. We need to check our work. So for silicon, we have 2 times 4, that's 8. Silicon over here, we just have 1 times 8, so that's 8. Hydrogen, we have 2 times 10, that's 20. Hydrogen over here, we have 10 times 2, that's 20. Oxygen then, we have 13 times 2, that's 26. Oxygen here, we have 8 times 2, that's 16. And the other product, we have 10 times 1, that's 10. So 16 plus 10 is 26. Here we have 26 and 26 oxygen atoms on both sides. Now that we've done that, we can say we have our final answer. Also, these coefficients are not divisible by any common number. So we can't divide 2 and 13 by 2. We'll end up reintroducing a fraction. So this is our final answer. Sometimes for these interfering coefficients, you'll have to change one, but then come back and change another. So some guess and check involved. Just follow the steps systematically and always be sure to check your work. So this next topic is similar to what we've been doing. We're going to write a chemical equation, but just from a description of the reaction. I mentioned how important naming and writing out formulas is going to be, so really make sure you're practicing that and keeping that really fresh in your mind. So how to name all those compounds and molecules, how to write all the formulas for ionic and molecular compounds. In this practice problem, solid magnesium hydroxide decomposes into solid magnesium oxide and gaseous water. So we're going to need to know magnesium hydroxide and magnesium oxide and the formula for water in order to be successful with this problem. Step 1, identify all the compounds and elements that are present in the reaction. We're going to have to know naming at this point. If, for example, carbon dioxide is mentioned, we should figure out that carbon dioxide, the formula for that is CO2. This is a molecular compound. That's why we have these prefixes here like di. Step 2, decide which compounds and elements are reactants and which are products. That will tell us what we write on the left-hand side versus the right-hand side. If we see calcium carbonate decomposes into calcium oxide and carbon dioxide, it's decomposing into these products, so calcium carbonate is going to be our reactant. For another example, ammonia is formed by these two reactants. So ammonia is formed by nitrogen and hydrogen. That means nitrogen and hydrogen are doing the forming. They are our reactants. Ammonia is forming, it's our product. Another really important part of this is remembering which ones are Brinkelhoffs. So if we hear nitrogen and hydrogen, we should think that they're Brinkelhoffs and not just write out N and H. With Brinkelhoffs, these exist as diatomics. So it'll be really important to know that nitrogen, we write out N2. Hydrogen, we write out H2. Bromine, we write out Br2. So please refresh yourself definitely on all of the Brinkelhoffs. Okay, so within this topic, we're kind of doing a culmination of a lot of topics we've talked about so far. Step 3, write the unbalanced chemical equation. So we're going to write our reactants out and our products out. These can be listed in any order. The order here is arbitrary. You could say reactant 1 versus reactant 2, or reactant 2 versus reactant 1. Also, at the end of chapter 2, I just quickly introduced these physical states. So if we know them, we should include that our compound is a solid, liquid, gas, or if it's in aqueous solution. For example, we're told here in our practice problem, we have gaseous water. That means we should write this in parentheses G. So we can write the state of matter if we know the states of matter. Sometimes we won't know, but sometimes we will be told, for example, like gaseous water. Then after we have this written out, we will balance the equation, following those steps from what we've gone through so far for either interfering or non-interfering coefficients. Let's do this for our practice problem then. Step 1, identify all compounds or elements that take part in the reaction. Hydroxide, hopefully this is ringing a bell. This is one of our polyatomic anions. Magnesium, it is a alkaline earth metal. So magnesium will form 2+ cations. Using the cross method then, magnesium will have a subscript of 1. Hydroxide will have a subscript of 2. We don't include that 1 there, but we do include the parentheses. So magnesium hydroxide, it's going to be really imperative that you're comfortable taking a name and writing out a formula. Magnesium oxide, Mg, still 2+. Oxide, that's oxygen with the ending change to IDE. Based on oxygen's place in the periodic table, it likes to form 2- anions. So here's oxygen, likes to form 2- anions. Halogens, remember, like to form -1 anions. Magnesium here is an alkaline earth metal. It likes to form 2+ cations. So be sure to review these patterns that we learned about previously. With the cross method here, we would end up saying Mg2 and O2. This simplifies to just MgO. Then lastly, we have water. So you should have this memorized, so H2O. Step 2, decide which compounds or elements are reactants and which are products. We need to go back to the description here. So solid magnesium hydroxide decomposes into magnesium oxide and gaseous water. So magnesium hydroxide decomposes. So this is our reactant. Then it changes into these products. It decomposes into magnesium oxide and water. So let's take the reactants and products and write out what we know so far. So I wrote up magnesium hydroxide here as our reactant and magnesium oxide and water as our products. We do also know something about their physical states. Solid magnesium hydroxide, solid magnesium oxide, and gaseous water. So solid, solid, and gas. I should have written MgOH2, really importantly. OH is in parentheses, 2 is outside the parentheses. Okay, so I needed to fix that, and then this is still a solid. So the next step here is balancing the equation. A good starting point would be magnesium or hydrogen, right? We don't want to start with oxygen. So magnesium shows up in just one reactant and one product, same with hydrogen. For magnesium now, we have 1 magnesium and 1 magnesium. So actually, as written, magnesium is balanced. Hydrogen, we have 2 hydrogens and 2 hydrogens. So again, hydrogen is also balanced. Lastly, oxygen, there are 2 oxygens. There are 2 oxygens. So oxygen is also nicely balanced. This will not always be the case. Fortunately, it worked out for this practice problem that it's already balanced as written. So those implied 1, 1, and 1 molar coefficients. Again, this will not always be the case, so be sure you're comfortable writing out these reactions and balancing these equations. Another topic you'll practice in ALEKS is writing a chemical equation from a molecular movie. For example, you might be able to see a collision happen where a chemical reaction has taken place. For example, a hydroxide anion, remember the name of this, collides with CH3Br. It could form this molecule and a bromide anion. Usually for reactive compounds and molecules, it doesn't take a collision to cause a reaction. Similarly, not all collisions lead to a chemical reaction. So as you look in ALEKS, it should be clear if we're witnessing a reaction happening or a collision where it doesn't result in a reaction. How can you tell? Well, for example, here we have these reactants and we have these products. So this is at the start and this is at the end. If some reactant is changing in some way to form a different product, then we do indeed have a reaction. To go from an image like this and an image like this into a balanced equation, we only want to look at the reactants and products that are different in the two images. So at the start, we can identify this here and this here. We identify this and this. We identify one of these here and one of these here. So what's changing is this, 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 and this. So as we're writing out the equation, we want to just focus on what is changing in the reactants and the products. From the key then, we would notice that this green is chlorine, white is hydrogen. This is 2 of these HCl molecules. Then over here, this is 2 chlorines, diatomic chlorine. So here's just 1 chlorine, and then this is hydrogen. If we're told what states of matter we're including here, then we do need to also write out the states of matter. If you're not told explicitly, then we might not know these, but if we are told them, you do need to include them in parentheses here. The last topic now for chapter 3a is writing the net equation for a sequence of reactions. So some reactions will happen in one step and then another step, and we end up just seeing either the individual steps, or sometimes we just see an overall or net reaction. So for example, here's one step, here's a second step. To write an overall or net reaction, we need to add these 2 steps together. So we're going to add together the equations from step 1 and step 2, or if there are more steps involved, we would need to add the steps from step 1, 2, 3, etc. So to start adding these, I like to take it step by step and substance by substance, or compound by compound. Here there's 1 water, there's another water, so that adds together to be 2 waters. So you might see it as H2O plus H2O, then we recognize that 1 H2O plus another H2O adds up to 2 H2O. You shouldn't forget the state of matter here either. Plus CO gas finishes up what we have on the reactant side. Then we have CO. Then we have 3H2 plus another H2. That adds up to 4H2. Then we have carbon dioxide remaining. Once we have this written out, we need to look at what appears on both sides of the reaction. So CO is the only compound that appears on both sides of the reaction. So with this and CO showing up on both sides of the reaction, we can further simplify this. So this is not yet our final answer. Because CO shows up on both sides of the reaction, we end up canceling this out. This leaves this as our final answer. We call something that shows up on both sides of the reaction an intermediate. So a compound produced in one step of a sequence, but it's consumed in another, are these intermediates. Carbon monoxide doesn't show up in our final equation. To see it here again, it's formed in one step, but it's consumed in the second step. Really importantly, that wasn't yet our final answer. This one is, because intermediates cannot appear in the net equation. So write out your steps clearly, really make sure that nothing is showing up on both sides of the equation in your final answer. Identifying these intermediates is going to be a key step in getting the correct final answer. We're at the end of chapter 3a now. Again, always let me know if you have any questions, you want to work through practice problems and office hours. Chapter 3 is one of the most important chapters in our whole semester. It really lays a lot of important groundwork. So let me know if you have any questions. I'll talk to you soon for the rest of chapter 3.